Welcome viewers, my name is Engineer Obaga. Today we want to be treating Prestress concrete beam design, and we are going to be treating the composite section. Unlike our last video, we did worked on a non-composite section, but today we want to be treating the composite section. Like we know, the composite section, it comprises of an in situ slab and a precast section. The importance of this composite section is widely used in construction of bridges. Most bridges, which are simply supported bridges, are usually constructed using a composite construction. And today we want to focus on the stresses in a composite section. All right, so in looking at the composite section, we're going to be taking a critical look at an inverted T-beam, which we're going to be using as our basis for composite sections. Now remember that the inverted T-beam is made up of the in-situ slab and the precast section. You can see the precast section has been shaded on the board, and we have the other part of it which comprises of the in-situ slab. Now, in dealing with composite section, there are two things we must understand about composite section design. There are basically two methods that are taken into consideration when dealing with this. The first one is a situation whereby we have the beam being constructed in such a manner that we have props. Props used as a support, a temporary support for the section while carrying out the construction process. In a case whereby you have props being used as a support for the section, of course, we know that this will help to reduce the stresses that are induced on the precast section, which is the shaded area. Remember that once the section is propped, the implication is that the additional stresses which are induced as a result of freshly cast concrete will be taken care by the props. All right, so additional stresses on your pre-stress section will not be incurred once the beam is supported by using temporary props. Okay, so but in another way, it all depends on the construction method. You can have a situation whereby uh, the beam is not propped, and as such, if the beam is not propped, when uh, the in situ slab, which is this area of the section, once it is cast, once it's not propped, what it means is that stresses will be induced on this precast section that is shaded. And when stresses are induced on this precast section, remember that in your initial analysis, if you do not take into consideration these stresses that are induced on this shaded area, which is the precast section, you are going to be having some issues, all right? Because additional stresses will be induced on this precast pre-stress section, all right? So the need for us to understand this is very, very vital in our design. So there are two basic uh, conditions for design. Number one, when the system is propped and when the system is not propped, like I've explained. So in a case where the system is not propped, we know that this is very common in most construction processes. The cost of propping is and the inconveniences in propping. Many construction engineers are always trying to avoid that, most especially in areas where you have high traffic and you don't want any kind of obstruction to the flow of traffic. You would not want to employ the use of props. Instead, you would like to carry out the construction process without putting temporary props. Okay, so what it means is this method of not propping is very common method which many people tend to use because of course it's going to save time and it's going to be more effective at the long run. So of course, in places where you have a river as an obstacle, you wouldn't be thinking of a prop as an option. All right. So we stresses due to uh, freshly cast concrete will be induced on this particular inverted beam, and as such, we have to consider these stresses. Okay. So now we are going to go on to look at several cases when it is not prop. Apart from the propping, in the design principle, we are going to be considering two basic principles. A system whereby we have the precast beam not propped, and when the precast beam is not propped, which I said is what we are going to do because it's commonly is a common method of construction. So if the precast beam is not propped and we have the neutral axis, the beam neutral axis lying within the precast section, we are going to have the composite beam if the neutral axis lie within the precast section. In other words, if your neutral axis lies within this shaded region. So anywhere from here down to here, if you have your neutral axis lying between these points, that is a case. All right. So we can have the system not propped and the neutral axis lying within this precast section. Alternatively, you can have the system not propped also, and you can have the neutral axis lying above uh, the precast session. All right. So these are the two possible design scenarios we are going to be looking at, and we are going to look at the various stresses that will be acting on this beam under these various conditions. All right. So the first condition we will look at is when the precast section, which is this shaded section, is not propped, which I let's go on and bring out some of the notations we are going to have for this particular section. All right. Um, let's look at the stress variation of this section. Now, so the first one we're going to look at is the one precast section. Precast section. Not if this is not propped, and we have the neutral axis NA. We have it to lie inside the precast unit. Neutral axis NA lies within precast unit. All right. So this is one of the cases we're going to solve for. So we'll look at the stresses for this. Now, in looking at the stresses for this, we need to look at the loading conditions for this. Remember that the two basic loads that are going to be acting on this beam are the live load and the load due to self-weight. And for load due to self-weight, we know that for self-weight, we are going to be having the self-weight of the institute section and the self-weight of the self-weight of the institute section, which is this unshaded portion, and the self-weight of the precast section, which is this shaded region. Okay, so if we want to do that, we can say let's bring out the notation according to method. Remember, all right. So we're going to look at the stresses that are acting on it. Now let's take a close look at the board. We are going to see uh, the eccentricity. We have the eccentricity, negative eccentricity above the neutral axis of the entire composite section. Now, taking a close look, you are going to discover that we have two neutral axes. We have neutral axis 1 and we have neutral axis 2. Now, neutral axis 1 is the neutral axis of the entire composite section, while neutral axis 2 is the neutral axis of the precast section. So if we look at it, we're going to see that the entire composite section is indicated with an asterisk, while that of the precast section is not indicated. All right. So looking at it from that perspective, so we have the E1, which represent the centroidal distance from the bottom fiber to the neutral axis of the precast section, and E2 represent the centroidal distance from the neutral axis to the top of the precast section. Similarly, also we have E1 prime, which represent the centroidal distance of the composite section with respect to fiber number 1. All right, and we'll have E2 prime, which is this E2 prime, which represent the centroidal distance of the section. Sorry, we have E3 prime. Sorry, we have E3 prime, which represent the centroidal distance of the entire composite section with respect to uh, fiber 3. And we have E2 prime, which is the centroidal distance from the neutral axis of the entire composite section with respect to fiber 2. So this is how we represent the sections in uh, the represent the stresses in the section. All right. So the first thing we are going to do is to calculate the fiber stresses. Now we have three basic load cases we are going to consider in this design. We have load case one. Under load case one, we are going to have our load, which is a load self-weight, load due to self-weight of precast section. We call that MDA, which is equal to moment due to precast section. All right. So the next we're going to have is number two. We are going to have load case two, which is going to be a combination of moment due to in situ slab plus moment due to precast section. So we can have that moment due to in situ slab as our MDB. So if we call that NDB, it means the load is going to be MDB plus MDA, which is the same thing as moment due to in situ slab MDB plus moment due to precast section MDA. All right, so these are the two load combination we're going to have. Then the third one, which is going to involve the live load, we're going to have a combination of the three load, which is ML. ML in this case, ML plus MDB plus MDA. All right. So these represents the entire load combination. Remember, in this case, our ML represent our live load, which also includes superimposed live load like your asphalt load and the rest. All right. So these are the three load cases that we are going to be considering in this particular design. All right. So the first thing we would like to do is to establish the stresses of this beam. We've seen the fibers. So we're going to pick the fiber stresses one after the other. Now the first one we're going to have is stress uh, on fiber number one. So for fiber one, we have the stress gamma 1. We have stress at fiber number 1. This stress is due to load combination 1, which is load due to MDA. That stress will be MDA over sectional modulus with respect to fiber number 1. Remember, your Z1 will now be sectional modulus with respect to our what? E1. All right, because E1 is that for the precursor section. Now, number 2, we are going to have stress. This stress is going to be a negative stress. So have the next is fiber 2 with respect to load combination 1. So let's get that of fiber 2. So this becomes fiber 2, which is Z2. Okay. Now, let's just look at the stress diagram of this particular system. I will draw the stress diagram before we continue on this. Okay. So we can see the stress variation on the board. So having looked at the stress variation, we have MDA plus MDB, which is our uh, in situ and our precast section. And we have the Prestress, and we'll have the stresses due to applied moment ML. And all these are the stresses we are going to be analyzing at this hour. All right. So now let's continue. Let's continue with the determination of the cable zone equations for this particular section, and as well the determination of the required pre-stressing force for to what we want to do is to establish the operative cable zone for this uh, section, and as well as the required pre-stressing force, both upper and lower limit of pre-stressing forces. And as well, we also will be treating the cover requirements. So take note that we are going to be having a graphical inequality for this section. Remember, by inequality, MDB plus MDA will be greater than our applied moment ML. So expressing it in a graphical inequality, we are going to do like we did in our non-composite section. Under load 1, we will still have it